Ever wondered what fuels your car or heats your home? Meet Alkenes, the hydrocarbons that power our world. Often overlooked, alkenes are organic compounds composed of hydrogen and carbon atoms in a specific array. They follow a unique formula signifying that for each carbon atom, there are twice the amount of hydrogen atoms plus 2. Their ubiquity is quite astonishing. Found in petrol that fuels our and natural gas that heats our homes, they are integral to our lives. But their use extends beyond just fuel. Alkenes are also present in everyday items like waxes and fats, making them quite versatile. This adaptability stems from the unique configuration of their atoms. Alkenes can form straight chains, branched chains, or even ring-like structures, each changing their characteristics and uses significantly. It's intriguing that the same molecular formula can result in such varied structures. The complexity and flexibility of alkenes make them a fascinating topic in the realm of organic chemistry. Their omnipresence in our daily lives only emphasizes their significance. Delving into the study of alkenes can lead to a deeper comprehension of the origin of fuels, their production mechanisms, and their environmental impact. This wealth of knowledge can be a stepping stone for innovative solutions to energy-related challenges. Now that we know what alkanes are, let's move on to how we name them. Naming alkenes may seem daunting, but it follows a simple set of rules. The International Union of Pure and Applied Chemistry, or IUPAC, has provided us guidelines for this. Let's dive in. First, identify the longest continuous chain of carbon atoms. This main chain is your parent alkane, and its name is determined by the number of carbon atoms it contains. For instance, a chain of 3 carbons is called propane. What if there are branches or substituents off this main chain? Name them based on their carbon count as well, but add a prefix methyl for 1 carbon, ethyl for 2, and so on. Now, number the carbons in the main chain from the end closest to a substituent. The substituent names, along with their carbon number positions, go before the parent name. For example, a methyl group on the 2nd carbon of propane is called 2-methylpropane. With these rules in hand, you can name any alkane you encounter. Alkanes can be more than meets the eye thanks to isomerism and conformation. Isomerism, to put it simply, is the phenomenon where compounds have the same molecular formula but different structural arrangements. In the case of alkenes, isomers become possible when we have 4 or more carbon atoms. For instance, butane and isobutane are isomers with the same molecular formula but different structures. Now let's talk about conformation. Conformation refers to the different spatial arrangements that a molecule can adopt due to the rotation about single bonds. Consider ethane, the simplest alkane where this can happen. Its hydrogen atoms can rotate around the carbon-carbon single bond, creating an infinite number of conformations. The most stable of these are the staggered conformations, where the hydrogen atoms are as far apart as possible, minimizing repulsion. As we can see, even simple molecules like alkanes can have surprising complexity. Despite their simplicity, alkanes have a range of interesting physical properties and chemical reactions. Let's delve into these fascinating aspects, shall we? Firstly, the physical properties. Alkanes are generally colorless and odorless. They are less dense than water, which is why oil floats on water. Alkanes are poor conductors of electricity, categorizing them as non-polar molecules. Also, the boiling and melting points of alkanes increase as the number of carbon atoms increase. This is due to the increase in the size of the molecule, leading to a greater surface area and thus stronger London dispersion forces. Turning to chemical reactions, alkanes are relatively unreactive due to the strength of the carbon-carbon and carbon-hydrogen bonds. However, they do undergo 2 key types of reactions: combustion and substitution. Combustion of alkanes produces carbon dioxide and water, releasing a significant amount of energy. This reaction is exothermic, making alkanes an excellent source of fuel. Substitution reactions, on the other hand, involve replacing 1 or more hydrogen atoms in the alkane with other atoms or groups of atoms. The most common example is halogenation, where a hydrogen atom is replaced by a halogen atom, such as chlorine or bromine, under the influence of UV light. These properties and reactions make alkenes incredibly useful in everyday life. Alkenes, like alkanes, are hydrocarbons, but with an interesting twist. They have a double bond, which gives them a whole new set of properties and reactions. The general formula for alkanes is CnH2n, where An is the number of carbon atoms. This double bond not only reduces the number of hydrogen atoms, but also introduces a significant feature known as pi bond. Let's consider ethene, the simplest alkene, for example. Ethene has 2 carbon atoms linked by a double bond and 4 hydrogen atoms. The double bond consists of a sigma bond and a pi bond. The sigma bond is formed by the overlap of 2 sp2 hybrid orbitals, while the pi bond is formed by the sideways overlap of 2 p orbitals. This double bond makes alkenes more reactive than alkanes, leading to a variety of interesting reactions. Alkanes are not just different in structure, they also exhibit different properties and reactions. Alkenes may look similar to alkanes, but they behave quite differently. Unlike their alkane counterparts, alkanes have at least one double bond between carbon atoms, which gives them distinct physical and chemical properties. Let's start with their physical properties. Alkenes are generally lighter than water and are insoluble in it. However, they are quite soluble in organic solvents. Their boiling points increase with an increase in the number of carbon atoms, and interestingly, alkenes with the same number of carbon atoms have higher boiling points than corresponding alkanes. Moving on to the preparation of alkanes, there are quite a few methods. One common method is the dehydration of alcohols, where an alcohol is heated with an acid, such as sulfuric acid, to remove a water molecule and form an alkene. Similarly, alkenes can also be prepared by the dehydrohalogenation of alkyl halides, where a hydrogen halide is removed from an alkyl halide using a base. Now let's delve into the fascinating world of alkenes' chemical reactions. Alkenes are known for their addition reactions, thanks to the double bond that acts as a center for these reactions. A classic example is the addition of hydrogen, also known as hydrogenation, where hydrogen is added across the double bond in the presence of a catalyst, usually platinum or palladium, to form an alkane. Alkenes also undergo halogenation, where a halogen is added across the double bond, and hydration, where a water molecule is added across the double bond in the presence of an acid catalyst. Halogenation results in a dihaloalkane, whereas hydration yields an alcohol. Then there's the addition of hydrogen halides, a reaction that follows Markovnikov's rule, which states that the hydrogen atom will attach to the carbon with the most hydrogen atoms already attached. However, in the presence of peroxides, this reaction follows the peroxide effect or the anti-Markovnikov rule, where the hydrogen attaches to the carbon with the least number of hydrogen atoms. Lastly, alkenes undergo ozonolysis, where they are treated with ozone to form aldehydes, ketones, or carboxylic acids, and oxidation, where they are oxidized to form epoxides, diols, or even cleave to form carbonyl compounds. As you can see, alkenes are versatile molecules with a wide range of applications. Their unique structure and reactivity make them essential in the world of chemistry.